Hi, now let's continue about cardiovascular physiology and especially cardiac cycle. The sequence of events that define this cardiac cycle and the role is to generate pressure which is onto the aorta, which is enough to produce a driving force for blood flow throughout our body. So let's consider cardiac cycle first. What is cardiac cycle? Which is let's take a look first. So this is a beating heart, and you can see these are right atrium and right ventricle, and left atrium, left ventricle. You can see the valve opens up and closes down. This is pulmonary artery, and pulmonary valve opens up, and you can see how the rhythmical this is. It's about like one hertz, right? And so we can consider a two phase of the heart. First, these ventricles are actually pumping, okay? This pumping, its phase is one, and then filling with the blood onto this chamber, that's a filling phase. So this pumping requires these cardiac muscle to contract, and that we call systole. And then the filling with the blood, which requires the cardiac muscle to relax, and that we call diastole. So here I want you to focus more on the left side of the heart, because they are both very similar, but in terms of importance, the left side is in charge of systemic circulation. So you can see this left atrium, and there's a mitral valve and left ventricle, and pass it to the aorta through aortic valve. So the cardiac cycle is really a pumping and filling of the heart by contraction and relaxation of the heart muscle. So let me go through step by step about how cardiac conduction and is involved in cardiac cycle. So first of all, automatic activation of action potential at the SA node, which resides within this right atrium. Remember that? That's where sinoatrial node exists. And that spreads through both atria first, because the atria has to contract first before filling to ventricle, and for ventricle to contract. So two small atria contract as a single unit, so that we call atrial systole. And the role of atria is only sending the blood to the next room of ventricle, so it doesn't require too much of a pressure. So the wall thickness is pretty thin. And because atria make sure to contract before the systole to contract, so it's good to have a delay in time. So that we call AV, atrioventricular nodal delay. And that allows the atria and the ventricles go through separate cycles of systole and diastole. And now let's see one more time. After late diastole, when things are relaxed, and now you see this gray colored one means a cardiac conduction. So that atria start to contract, so that atrial systole, and then once the blood fills into the ventricles, and the ventricle will contract. Okay, that contraction eventually opens up the valves to the outside. That's we call a ventricular ejection. And that after the ejection, it will relax back. So that ventricular relaxation. So that contraction of the left ventricle, we call it isovolumetric ventricular contraction. And why do we call this as isovolumetric? Meaning that the volume doesn't change. Okay, this ventricle has two valves, especially left ventricle, coming from left atrium to left ventricle. There's a mitral or bicuspid valve. And the left ventricle to the aorta, there's an aortic valve. So when two valves are closed, the volume won't change because it's a liquid. So that's why we call isovolumetric ventricular contraction, which means both aorta or aortic and mitral valves are closed. And when it contracts, the pressure builds up. Eventually, it causes the aortic valve to open and ejecting blood into the elastic aorta. The aorta, as being elastic, means it keeps the pressure to transmit that pressure through systemic circulation and initiating blood to the rest of the body. So for that, we divide this cardiac cycle into phases, 4 phases of action within the left ventricle during a cardiac cycle. So let's think about it first. First, upon the point of view of the left ventricle, which is one of the most important pump in the heart, and the left ventricle has an inlet valve and outlet. So thinking about inlet and outlet point of view, first filling phase will require inlet to open. So inlet to open while outlet is still closed. Remember, valve is only one way. So one way it's open, the other way it closes down. And then because it's closed, now the ventricle starts to contract. That's because the volume will remain the same while pressure builds up. So that's both inlet and outlet is closed. That's why we call isovolumetric contraction. And then at some point, it'll open up this outlet valve. So while inlet's closed, outlet will be open. That we call ejection phase. And then afterwards, so the pressure will come down until it also closed outlet valve again. And then it'll relax. So this, again, both valves are closed and the muscles relax. So the volume's the same while the pressure comes down. That's called isovolumetric relaxation. Here in left ventricle, of course, inlet is here, mitral valve, while the outlet is aortic valve. So the goal of this cardiac cycle for the left ventricle is to generate enough of hydrostatic pressure within the aorta so that, this high pressure is a driving force for the blood throughout the circulation. And that's having some sense of the parameters here. So the heart size is about our fist, which is about the center and towards a little left of our chest. So left ventricle volume is about 120 milliliter at the end of diastole, and while it squeezes down, and that remains about 50 milliliter at the end of the systole. Let me bring, this is about 300 water bottle, and so the amount of this is about 120 milliliter, so that diastole of the left ventricle. Let me drink about 50 milliliter here. Okay. So after drinking 50 milliliter, then the changes of the volume here during one beat, we call it as a stroke volume. So that's 120 minus 50 is of course about 70 milliliter of, this is the volume of one stroke, the changes. And while during this, what's the pressure change? This aortic pressure change, as you remember, it's about 80 millimilli Hg to 120. So that's 80 is about the end, the diastolic pressure prior to ejection, and the systolic pressure during ejection, it gives the highest pressure, just 120 millimilli Hg. As a home exercise, I'm giving you one simple example of cardiac output, which means how much of the heart actually pushes the volume of blood per minute. For a person who have heartbeats about 70 beats per minute, which is normal, with a stroke volume of 70 milliliter. So 70 milliliter per beat, let's say, then you multiply this and this, it's about 5 liters per minute. So that's a cardiac output. So now we are ready to get into detail of this phase. So relax and contract of heart muscle while refilling and pumping the blood. So let's take a look at the heart beating first. So this is pretty complicated, so we divide that into, let's start with filling ventricular filling. So you look at this from atrium into the ventricle, and that we call ventricular diastole because it's filling. And then the atria has to contract, to push, so that we call atrial systole, and that atrial systole can be detected in ECG diagram as here as a P wave. And then what happened? The atrial systole that fills into the ventricle, and then when the blood inside the ventricle, the pressure builds up, will close down this mitral valve and or atrioventricular valve, and that closes down, makes it a closed system, and then the muscle will contract, so it will increase the pressure, so that isovolumetric contraction. And then while it increased the pressure, at some point at the end, it will open up this aortic valve or pulmonary valve, which we call now ejecting the blood, so ventricular ejection. So this is the main part, main action of the heart. So that becomes the most highest in terms of electrical activity, and it shows to our ECG as a QRS complex. Once you eject, then it gives the pressure drop until it closes down this outlet valve, and now it will relax. So that's called isovolumetric relaxation. And hopefully this cycle goes. And while this atria side, only this part is contracting, so that's atrial systole, while the other part is quite relaxed, so atrial diastole. So now I want to get into a little more deeper into cardiac cycle of the left ventricle in terms of both pressure and volume aspects. So first, let's look at the left ventricle. So this inlet to the left ventricle is called, outlet is called aortic valve, and inlet is called mitral valve. So in terms of left ventricle, it's connected to left atrium and aorta. And the valves on and off just depends on which pressure is higher. Okay, so in that regard, let's see the pressures of left ventricle inside, which is depicted here as a blue, which of course has undergoing this contraction, the pressure will be building up very high and low. While the atrium, which is connected to the left ventricle, the pressure is only not that high. So this is atrial pressure, here in yellow is here. And then the aorta, which of course, when aortic valve opens, it's pretty high pressure. So aorta pressure is in red. So let's look at one by one here. So initially, mitral valve is left atrium is higher pressure than left ventricle. So when this filling effect, the mitral valve is opened. So for that, you can see this left atrium is only slightly higher pressure, which makes sure atrial valve opens. But when because of the filling up, the pressure of left ventricle starts to build up. At some point, it's higher. What that means is atrial valve now stop. So atrial valve closes, and then while the ventricles start to contract, and both mitral valve and aortic valve are closed. So now the pressure will build up like this until the pressure is so high that higher than the aortic pressure, where this crossing over happens, what happens? That aortic valve now starts to open. So aortic valve opens and the ventricle keeps contracting. So an ejection happens, and while it contracting until aortic pressure and ventricular pressure crossing over. And that's this point. It's a little unclear, but this point where aortic valve closes down. And what happened? Both valves are closed down and the ventricles start to relax. So that part, the pressure will brings down until now this left ventricular pressure is becoming lower than atrium. Then the mitral valve starts to open. And this part is now we keep relaxing. So the pressure is kept down, and this is diastolic. So you can see one by one throughout the cardiac cycle, this pressure changes or differences makes the valve, mitral valve closes and open, aortic valve opens and closes. And let's look at this in terms of pressure and volume together. So let's see, as I alluded here, mitral valve closes down over this point number 1. So this y-axis is left ventricular pressure, and while we also consider left ventricular volume, how the volume changes. So when mitral valve closes, both mitral aortic valve are closed. So it's closed system. Now the volume, it's pretty high, but it doesn't change during, during this systole, ventricular systole happens, then pressure builds up until aortic valve starts to open due to this crossing over of aortic and ventricular pressure. And then it ejects so that pressure is building up, while because the volume, it's ejecting phase, this end diastolic volume start to decrease until this aortic valve start to close. Then what happened? Now both valves are closed. It's closed system again, while the ventricles relax, which means the pressure comes down while the volume stays the same. So until again mitral valve starts to open, then the filling happens. So the ventricular volume becomes higher because of the filling, and due to mitral valve opens and blood coming from left atrium to left ventricle. So now you can see the relation between left ventricular pressure and left ventricular volume. And this part of BC is systole, left ventricular systole, and DA is diastole. And of course, A is atrial systole. So from this 1, 2, 3, 4 phase, now we can draw a diagram between pressure and volume, which is very important in terms of mechanical energy aspect. So we can consider this one as pretty high, high volume, while mitral valve from left atrium to ventricle is closed, okay? Mitral valve closed, then what happens? Now ventricle starts contract, and the volume doesn't change while pressure builds up. So this is isovolumetric contraction until this aortic valve opens. Now ejection happens. While ejecting blood, the volume, this x-axis volume starts to decrease until this aortic valve closed down. Now both valves are closed down so that it's phase of the left ventricle to relax while it's a closed system. So the volume doesn't change while the pressure starts to decrease until mitral valve opens. And then mitral valve opens as the blood starts coming in from the left atrium. So the volume will increase. So this 1 to 2 is called isovolumetric contraction. 3 to 4 is called isovolumetric relaxation. Here I said. So by knowing this pressure volume loops, we can now start to consider the energy aspect. So mechanical analysis of the cardiac cycle can be done by drawing this pressure on Y and volume and left ventricular volume on x-axis. So the end point of the systole, which is point A, and the mitral valve opens, and the ventricle is filled from the atrium, and first passively A to B, and then actively start to actively press, fill until point C. And then isovolumetric contraction of the ventricular wall makes dramatic increase in pressure at a fixed volume, which is depicted here as C to D. And then aortic valve opens and the blood is ejected from the ventricle to aorta, which is D to EF. So now the volume goes down until this aortic valve closes down. So now isovolumetric relaxation returns the ventricle back to the starting point, which is A, at the end of the systole. So you look at it here, the volume of this AFA and CD, which is end systolic volume and end diastolic volume, that difference is defined as stroke volume. And you can see this aortic pressure from about 80 to about over 120. So now think about the work of the heart on the blood. So what is work? Work in physics is typically defined as if there's a mass, you push the mass with a force, and then that force makes a displacement x. So the force multiplied by displacement is defined as work. But in involving the fluid, the force, usually we don't use force, but the force per unit area. So that force per unit area is defined as pressure. And to make this area the same, area times displacement is area times displacement involves the volume change. So pressure times change in volume is now you can calculate as a work. So during the one net cardiac cycle, what is the work for the blood to do on the system boundary of the heart? Is the work done by the heart during the ejection period, which is E, F, G is the ejection period, and then work done by the blood on the heart during the filling period, which is A to C. So the work as a net is D to F of the pressure multiplied by volume change minus A to C, which is a pressure pressure times volume change. So that is effectively the area of inside this. And here, because this is going towards the left-hand side, so the work of the net of the blood will come out to be minus. Here's a homework exercise for you to just simply try it out, is try to calculate the work done by the heart during one cardiac cycle. Then you can calculate one cycle, how much of work does the heart need? And you can easily calculate the heart beats about 60 times per minute, one heart. And throughout the day, how much work the heart need to do. Then you may calculate how much food of the energy source you have to intake to keep at least the heart go. So for those who are more interested in here, I have this reference which also shows the QPRS, PQRS, and T electrocardiogram, which is coordinated with the cardiac cycle and the volume. And also there's another drawing, so you can actually take a look deeper into here. So let's summarize. The cardiovascular system is a pump, which is the heart, and which circulates specialized fluid, which is blood, through a system of branched vessels. And the blood is a fluid composed of the cells in a protein-rich fluid called the plasma. And that cells include mostly RBC, red blood cell, about 40%, why that transports oxygen to the tissue. While there's also another type of cells called white blood cells, which is involved in the inflammatory response and immune function. And also there's a platelet, which is important for the blood clotting. And many biophysical properties of the circulation can be understood by engineering model as systemic approach. So for example, fluid flow in the cylindrical tube provides us an insight about how much of resistance or will be required depending on the diameter of the vessel. So that in a circulatory system, we realize the sudden decrease in vessel diameter through the arterial and capillary is responsible for most of the pressure drop in the body fluid system. And the heart, lastly, is equipped with a muscular wall that contracts to pump blood from its chambers, which are both atria and ventricle, to other parts of the body. And the heart contracts rhythmically. The goal is to create blood pressure, especially at the aorta and pulmonary artery, which drives the blood flow throughout the system and throughout the pulmonary lungs. So with that, I'm going to finish here, and thank you very much for your attention.